Okay, hey everyone, welcome to this webinar. This is a slightly different one. This will be an introduction to fNIRs analysis using slightly newer, relatively newer toolbox called MNE. And we at NIRx, we like the idea of giving our users the option to choose the platform of their choice. We do this by providing data in open source format, so allowing you to analyze your data with our analysis software as well as any open source platforms. And we'll take a look at one such relatively new entry, the MNE toolbox, which will be presented by one of the developers, one of the most active developers, I would say, Dr. Robert Luke. Before I introduce Rob, let's go into some logistics. So I'm Mahipal. I'm a scientific consultant at our Berlin office. I'm joined by my colleagues, Christina and Amy, who have been working very hard in the background to bring this webinar to you. They will still be working. They'll collect your questions. So if you have any questions, please put them in the questions box in your GoToWebinar panel. Few more considerations. We absolutely love to hear from you. For this webinar, you will be muted. As I said, any questions, please do write them in the GoToWebinar panel. If you are not able to take all the questions today, we will make sure that we get back to you offline. Also, all these webinars, all the webinars we do are recorded, and you can watch them later by going to our website. Upcoming webinars are also notified through our website. For any other questions, for any other follow-up questions, you can always write to us at consulting@nirx.net. Now, coming to our speaker, I am very delighted to introduce Dr. Robert Luke. He is a research fellow in the Department of Linguistics at Macquarie University in Australia. And he is an electrical engineer with background, has a Ph.D. in cognitive neuroscience, and currently he does auditory neuroscience research, investigating the basic mechanisms of hearing. And his interest in fNIRS began with his work with people who wear cochlear implants. And Rob, that being said, the floor is yours. Please talk about the MNE toolbox.
Excellent. Thanks for having me. I'll try and share my screen. How do I?
Amy will make you a presenter in a moment.
Thank you.
Yep, you should be able to do that now. Otherwise, I can do that again.
If you could try it again, please.
Yep, one moment. And
there's also a tiny button, Rob, says share screen. Maybe you're able to do that.
There we go, show my screen.
Nice.
Yes.
Good, all right, thank you. And then I'll put up my slides. And so thanks for attending. We'll go through sort of the introduction to fNIRS analysis with the MNE toolbox today. And well, first I'll describe what is the MNE toolbox. I'll go through what the sort of features and the capabilities that it has, and I'll show you the website that you can find out more details about these different features. And then I'll show you how to get help and how to learn things, so where all the documentation and about the MNE community. And then we'll go through a live coding example with the toolbox. So we'll start now with with what is MNE. So MNE Python is a leading sort of MEG and EEG analysis toolbox, which has been around for many years, and I'd say it's got a very strong averaging sort of analysis pipeline. And that's and I come originally from an EEG background, so that's where my knowledge of this toolbox came from. And then MNE is also so the MNE NIRs is also built on the NI-Learn toolbox, which is an fMRI analysis toolbox, and that's got a really strong GLM capabilities. And so what we've done is we've taken these two toolboxes and combined them to provide like an fNIRS analysis toolbox. And so while MNE NIRs is quite new, as Mayapal was sort of saying, it's built on quite an established code base. So we'll go into sort of the details in a second, but there's been, you know, many years and many developers. So over 250 people have contributed to MNE Python, and it's published and it's been well cited. So that's the sort of building blocks which we worked upon to build MNE NIRs. And so you could sort of think of MNE NIRs as a packaging, and within that packaging there's MNE, there's NI-Learn, and the stats models package, which is where all the stats comes from. And what we've done is we've wrapped it all together and we've given it some fNIRS specific features. So there's things that exist in fNIRS which don't exist in other neuroimaging techniques like short channels and long channels. So these things are quite unique, and that's what we packaged within the MNE NIRs toolbox. And so maybe this would be a good time to ask people. We have a few polls today. So we were going to, the first poll I think was going to be sort of what software do people use currently. Was that the first one? Did we launch that one?
Yeah.
Oh, there we go.
So we can launch that.
So this is going to help me while you guys are filling this out. This is going to help me to pitch or to sort of what level of detail I'll give in the example later. I've lost my mouse.
Yeah, you won't be able to see anything until the poll closes. So we'll just let a couple more seconds, people to all vote. Anybody else is still, we're up to 75% and going once, going twice. Close the poll now and share the results with you.
Okay, so most people have used the NIRS toolbox, and then Homer as a second, and then surprisingly MNE as a third. Okay, so not so rare. Maybe it's a very specific group of people that have joined us today. All right, so moving on. So what are the features of the MNE and MNE NIRS toolbox? So we can load NIRx data. I guess that's the first thing I should talk about. So we can load both the raw sort of NIRx file format as well as SNRF, which the Aurora software exports. And so that includes the 3D locations of sources and sensors, but we can also do 3D digitization with like a polymer system or something like that. I'm not going to go through all of these, but you can see that we've got both an epoching and a GLM analysis pipeline capabilities, including first and second level sort of covariate processing and mixed effects models, your standard pre-processing. So if there's any sort of, questions on these topics, we can sort of touch on them today while I'm going through the example. And so what we won't be touching on today, which are kind of your more advanced topics, but are things like, so I've taken some figures from the different examples, which I'll show you on the website in a tick. So we can sort of plot the results on a head. So as you can see in the top left, we can analyze the connectivity. So there's, we can plot the connectivity between different sources, different channels, sorry, or by brain region. There's also machine learning capabilities like decoding, which we won't touch on, but these are all sort of advanced topics which you can find examples on the website. But what we're going to start by looking at today is I'm going to show you the MNE Python website, and then discuss where you can find the details to install this software. So let's go through those one by one.
Rob, sorry to interrupt. This also seems like a good time to take our second poll, which is about the challenges people face.
Excellent.
And then you
Yep.
could maybe highlight those points in your talk.
Yep, great.
If you could there.
Yeah, here we go. So everyone can, or maybe everybody's completely satisfied.
And if you have missed any options, please do write to us. We could only insert 5 options with the polls.
So just a couple more seconds. We'll let everybody have their chance to share. And I will close the poll now. Drum roll, please.
Okay, so the biggest complaint seems to be, or not complaint, challenge, seems to be a lack of support and resources, followed by 2 basic, and then 2 advanced. So we'll aim for somewhere between 2 basic and 2 advanced today. How about that?
Sounds great.
Well, on the resources, the top response there. So this is the MNE website. This is the front page, and you can see that it's a well-supported and well-funded project, and it has what I would say like second to none documentation. So there's a few, and I'll just quickly walk everyone around. So if you click on the documentation tab up the top, and then if you hit the tutorials button on the left, you can see there's a long list of tutorials here. Excuse me. And each of these tutorials is on a different topic. So I'm just going to go into one of the fNIRs tutorials, and you can see that is a quite well documented. You can see the output of different code. These are all automatically regenerated each time the code is changed to make sure it still works. And we're going to go through one of these today. But another little tip that's quite handy is if you wanted to know about a specific function. So let's say you were interested in the optical density function, you can simply click on it and it will take you to the documentation for that, that function, and it will explain to you the parameters and the input and the output. And then below that, it will show you the different examples which use that piece of code, so you can see it within the context of an example analysis. So if we were to click on this, you'd see that there's another example which used that same optical density code. And what else is useful? So this is the MNE package, and it handles sort of your basic generic concepts. But for anything specifically fNIRS related, there's a second website which you should go to, which is the MNE NIRs package. And this is the one that we'll work on today. So it also has an examples tab. Similarly, it has examples, but these are now all fNIRs specific. So they are relevant to today's discussion. So we've got simulated GLM analysis, individual level GLM analysis, group level GLM analysis, FIR GLM analysis, waveform averaging, group level waveform averaging, etc. So you can have a look through these. And then, sorry, the last thing I'll point out is if you're interested in this topic, so let's say you wanted to do a group level waveform analysis, but you haven't installed Python on your computer, but you just want to give it a try. If you scroll all the way to the bottom here, you can launch what's called a binder notebook, and I'll click that. And what that's going to do is it's going to start up some Python in a cloud server, and it's going to allow you to actually run through this notebook and change values, and you can do your analysis without ever needing to install Python or MNE on your computer. And this is what we're going to use today so that you guys can follow along with what I'm doing, hopefully. So, okay, I'll go back. I was also going to show you how to install MNE. So we'll leave this for now. To install MNE, you go to the install instructions up the top here, and then you would go to installing MNE Python, and there's a long list of instructions with different instructions specifically for if you're using a Mac or a Windows computer. So if you follow these point by point, hopefully it would get installed correctly. If it doesn't, if something happens along the way, which, you know, we might have missed out some documentation, I'd recommend you head to our discourse forum. So up the top here, there's a little talking box. If you go there, this is our help forum, and you can see that there's about 2,500 topics that have been discussed, and there's about 73 new discussions per month. So it's quite an active forum, and you can see that people have been on it 2 hours ago, 7 hours ago, 12 hours ago. So if there's anything that's unclear, this is the place to ask the question. And the last kind of community level topic that I would discuss is that, as you can see up the top here, we have an office hour. So that's when we have a live video chat like this, and that's usually every other week, where we can give you a hand. So if your question isn't answered here and you just want to talk to someone, these are the office hours that we have. All right, so I will close this. And so today, for the rest of this talk, how long do I have? I'm 15 minutes in already. So we're going to give a little live demonstration of MNE that I hope you can all follow along with. There's a link at the bottom here, which if everyone who wants to follow along could click on that, it will open up an MNE Python notebook for you to follow along with. Or if you probably can't click my screen, can someone put it in the chat? I think I put it in the chat before. Yeah, so what we'll
I'll do that.
Yeah, if you could, thanks, Amy. And then if someone could let us know if it's working or not. So I'll click on that myself. So you should see this this notebook start up, and you can follow along and make the changes with me today. And so what we're going to do is we're going to go through a basic analysis. It's some data that I collected where I'm tapping my fingers with my right hand or with my left hand, and there's also a control condition. But the point isn't really about the analysis. It's more about demonstrating to you the different features of the toolbox. So and also to give you an introduction to Python programming. So actually now's a good time while that's loading up for everyone to ask the last poll.
Yeah, Amy is going to bring that up now.
Not that one. You want to walk us through the levels?
Oh yeah, so I'm gonna give you a live demonstration of how to use MNE to analyze your fNIRS data, and it's going to be in the language of Python, so that's a programming language. And I wanted to know, are you a 5 out of 5? So are you an expert in Python, or are you a 1 out of 5 where you've never used Python? So if you could sort of rank yourselves there, and then I'll know how to pitch the presentation today.
Yep, we've got about 3/4 people. So I'm going to close the poll now and share the results.
Okay, so most people haven't used Python, and a few people have sort of given themselves the middle of the range. So that's great, that's handy. So I'll provide a slightly more introduction to Python then, and we'll use the example we'll use will be a waveform analysis, and we'll try and go from the raw data through to some sort of statistical conclusion, and save sort of GLM processing and more advanced stuff to the second seminar. There's already been a best practices talk, and so I'm going to do some strange things just to demonstrate functionality. So we might add noise just so I can show you some noise reduction or something like that. So so be aware of that, and ask questions throughout. It would be, you know, more fun for all of us. So with that, I'm going to end my PowerPoint presentation. And has anyone successfully got to the point where they see this on their screen? So this is what's called a Python notebook. It's a Python notebook server. So Python is a programming language, and it can be like MATLAB, where you have, I'll give you an example. So you can use an editor like this, which looks just like MATLAB, and it's very codey, and it's all about scripts. But I find for tutorials and for teaching that this sort of notebook form works quite nicely. So has anyone managed to get to this screen?
We're hearing that, yes, a couple people have been able to. The chat function's not working, so I just apologize about that. We'll work to get it fixed.
Yep. So if we, to follow me along with me today, if you click on the examples link, and then you click on this MNE NIRs demo 1, it will open up today's tutorial. And so you should see at the top, I've just provided some links to some of the websites that I showed you before. And then what we're going to do today is we're going to go through some Python basics, how to load your data, how to view the raw data, how to manipulate it. So if you want to take just some channels, or if you want to crop out some data, and then your standard processing, so conversion to hemoglobin, or how to calculate scalp coupling index or other quality metrics, and then a brief waveform analysis. And so the way that you use this code is in these gray boxes here is the code. And if you want to run it, you press this little run button up the top and it will run that line of code. And you'll get a little star while it's running. And then when it's finished, it should come up with a little number next to it. And because it's in the cloud, it can take a little second. So there you go, that's successfully ran. So I'm going to leave you all to walk through this cloud version with me, and I'm just going to use my local version so that we don't have any issues. So this is the same script that you have, but we're going to work through it together. And so we're going to start off with the Python basics. So we have different packages that we're going to use. This is the same as you all know what a package is. You've got your homers and your NIRs toolbox. And we're going to import the MNE package, and that handles, like I was saying before, your averaging and your filtering and all the standard things that exist for both EEG, MEG, fNIRS. And we're also going to import the MNE NIRs library. So this is the fNIRS specific part. And so for every script, we basically always load this. And I'm just going to restart, so we start fresh. And just to make sure we're all working together. So I'll run that one, and you can see it's running. And we're now at the same point. We're also going to use a few other packages, and don't get panicked if you see a slightly different import. This is just another way of importing a package. And so that's how we import packages. Another useful thing is functions. So functions, this is a function. So here we're just going to make some zeros. So we have an argument inside the function. This is just like MATLAB. That's my point here is to sort of say, you might not have used Python before, but don't worry. We just have functions which return things. So we asked for 4 zeros and we got 4 zeros. And the other thing we're going to do is set the 3D backend. Now, because this is a notebook, we want the pictures to sort of appear within the notebook. And so we're going to tell it to put all the plots in line so it looks kind of nicer, and you'll see that in a second. So that's the Python introduction. No questions have come through yet. So we'll get on to the fun part, how to load your data. So we're going to import 2 more libraries. The OS library, which just tells you how to deal with files and folders. And then we're going to ask it to give us the example fNIRS data set that we're going to use. So this is my tapping data set, which I was telling you about before, and it lives here. So if you just give a variable name, it's just going to print it out. So it's easy for you to see the output. And we're just going to look at participant 1. So this is the full path here. And to load NIRx data, we use the MNE library, we use the input-output module, and the read raw NIRx function. So this is quite, a lot of you said that you'd use the NIRs toolbox, and this is a very similar sort of concept. So there you go, like NIRs toolbox.io.read NIRx. This is very similar, and then we pass it the path, and then we give it some arguments. So we want it to be verbose. During this tutorial, I want it to spit out lots of extra information for you, and we want it to load the data. So it's as simple as that. So it's now loaded the data, and it's put it into this raw intensity variable. Has anyone successfully done that?
If I may interrupt here, there's a question on data formats. someone is asking, is there an option to bring data into the BIDS structure?
Yes, yes. So if to get it into BIDS, there's actually a little side project I've got which does that, and I can provide a link at the end, and I'll show you if your data is in BIDS how to read it right now. So for those of you who don't know, BIDS is a common format for how to store your data, but not the file format like SNRF, but more what folders to put it in. And if you've watched the NIRx tutorial about the NIRS toolbox, you have to have a very specific hierarchy for your folders, and this is a standardization of that, so that all the different software toolboxes could use the same folder hierarchy. That's what BIDS is. So to change to something else, if you wanted to load a different file format, you would these are all the different file formats that you can. So there should be a read raw SNRF in here, for example. So there you go. There's a read raw SNRF, but we're going to stick to the read raw NIRx today. And so once it's read into this raw intensity, how do we know that it read in correctly? Well, we can look at that variable, and it will tell us the information and format it in a nice way. So this was recorded November 2nd, 2019. There's 56 fNIRS channels and no EEG channels. So this toolbox is capable of doing joint EEG and fNIRS, which I think is becoming more and more popular. And it will also print out some standard information like the sampling rate, the file name, and the duration of the recording. So this is really handy to know, did I load the right file, basically. And then if you want to drill down into even more information, so we can also get the NIRx also saves like the participant's name and their gender and their age. So that is stored within the info. So you can go rawintensity.info and ask for the subject info, and it will report that back. And this can be quite handy in the more advanced topics, like in the second level mixed effects models. So we have access to this information, and you can include that in your models, which we won't do today. If you want to get the data, so you would call the get data on that raw intensity, but we'll probably never use this. This is sort of more just letting you know how things work. So that would return, the shape of that would be, there'd be 56 channels and 23,000 data points. All right, and so I think that's that's how you read your data and how you sort of probe the underlying parts of that data. So how do we use that? How do we go forward? So we had a couple of questions before when people registered. And so a few people asked about sort of 3D locations and positions. So I'll show that in a second, but it's sort of a more advanced topic. So I won't go into details, but I'll just we'll sort of touch on that. So if you want to look at if you want to make sure that your sensors are loaded correctly, you can take your raw intensity data and you can ask it to plot the sensors, and it will plot a little head. And this is each dot here represents a channel. So in this data set, I put some channels over the left motor cortex and the right motor cortex. And I was hoping that they would light up when I was tapping my fingers, and that they wouldn't light up when I wasn't tapping my fingers. You can also, there's sort of 3D capabilities here. So this is a bit more advanced. So I'm not going to sort of explain. This is more due to a question, but you can plot the positions in 3D here. So if you do this, red represents a source and black is a detector, and yellow is the midpoint. So that's what we call the channel location. So that is available, but I'm not going to go into details because it was just a question in the registration questions.
One more question which seems relevant at this point, which is, any hints on visualizing each step of the processing chain to see effects of parameter changes on output? So is it possible to visualize major steps?
The data? Yes, it is. Yes, it is. So let's, yeah, I'll do that in about 2 or 3 steps. So another, yeah, so when your data is loaded, we've seen that it loads in the sensor locations. We also load in the triggers, or what we call them annotations. So they can be handy to plot as well. So so we can plot those annotations here. So the data just knows that it gets a trigger 1, trigger 2, 3, and 4. We need to inform it that 1 is control, that 4 is left tapping, 3 is right tapping. And then we can just plot this here by using this MNE.vis. So now we're using the visualization capabilities of MNE and ask it to plot the events. And we need to give it the sampling frequency as well. And it now tells us that at the beginning of the experiment, there was this trigger, which represents the end and the start of the experiment. And you can see that there was a number of control and some tapping. So that's sort of the triggers, or the annotations as we call them. And then somebody asked about loading BIDS data. So to load BIDS data, you use the read raw BIDS function. So not read raw NIRx, but read raw BIDS. And if you do that, I think this is what Michael was asking for, we can now look at the raw data. So
there's
two
one
parts.
more question, Rob. I'm sorry to interrupt again. It seems relevant, just came in. A source of layout files for different optode layouts would be very useful. Do we have to create it by hand if we use a specific layout?
So if you create your montage with the NIRs software, then it's automatically read. So that information is saved with your NIRx recording, and the MNE software will read that in accordingly. So you don't have to. I mean, all I did above is I just said read raw NIRx or read raw BIDS, and it extracted the relevant source and detector locations. So you don't have to manually create that if you use an earsight, which I assume everyone is doing if we're on a NIRx seminar. Yeah. Yeah,
it is needed for data acquisition. And the probe info file is stored with every data set. So that's why I guess MNE reads it automatically.
Yeah, so we read the probe info file automatically. And so here, to look at your data, so now we're getting into the fun part. What I'm just doing here is I'm setting the default figure size. So I'm telling it I want a 10 inches by 10 inches plot or something. So that's what this part here is. But what's more interesting is this. So we have our variable, our raw intensity data, which we read. And if we just say dot plot, it knows how to plot that data. So it knows the best way to plot that data. And we can tell it, do we want to look at the whole measurement or just the first 5 minutes? So here I've just asked for 300 seconds, and I've asked it to give me all the channels. So you can see in this plot here, along the vertical axis, we have all the channels, so source 1, detector 1 for the 2 wavelengths, all the way down to source 8, detector 16. And along the bottom here, you can see that we're only looking at the first 5 minutes of this quite long recording. And each of the colors here represents a trigger. So this experiment started with 2 controls, then a tapping with the right hand, and then a control, and then tapping with the left hand, and so on. And you can see the heart rate in some channels. So this is how you would look at the raw data. And you can always call this plot function after each step. So the question in the registration was, how do I visualize each step of the processing? So you would do a step of the processing, and then you would call this again, and you can look at how it's changed. I think does that answer the question?
Yes, I think so.
Okay. And let me know if I'm moving too fast or too slow. So you're all running this in the cloud, but I'm running this locally. So I can actually show you that these plots are actually interactive. So if we now tell the computer that we want to do interactive plots, which is this command here, matplotlibqt, and I run exactly the same code as above, what happens is it now gives me an interactive plot, and I can sort of drag through the recording, and I can look, I can sort of check where there's movements, and maybe there's a little artifact here. So a lot of the plots that I'll show you in this introductory webinar also have an interactive component, but I felt that was sort of more advanced, and I'll leave that to the next topic. But just letting you know that the capability is there. And you can also do things like, if you see a bad channel here, if you click it, it will be removed from further analysis. But we're not going to go into that just yet. So I'll turn that off again. We just want our plots to appear as normal. So that's sort of how you read your data and how you just look at where the sensors are and you look at the raw data. Now I'm going to go into how to manipulate your data. So some basic things. So first of all, I like to work on a copy of the data. So we're going to do some funny things here like resampling and cropping. So what you can do is if you run this cop.copy, it just makes a copy of the data, and then you can play with that copy, but you've always still got your original data. So let's work on a copy. So now we have this data, which I'll just call raw, and it's the same as before, the same 56 channels, same 7 Hertz. And so it's handy to resample your data. So MNE has lots of filtering and resampling capabilities. So to resample to 2 Hertz, you would simply say raw.resample2, and you can see that now the sampling frequency is 2 Hertz, whereas previously it was 7.8 Hertz. And because we're working on a copy, the original data still exists and it's still 7.8 Hertz. So that's quite handy. You might also want to look at the annotations. So like I was saying before, we call triggers annotations. And you can see that there's 90 annotations, there's 30 controls, 30 tapping left hand and 30 tapping right hand. But it can be handy to see like a whole list in the order. So you can ask it to give you the annotations. So you want the raw data, give it the annotations and convert that to a data frame so it's easy to read. And then this is what we have. So it's saying, the first annotation was at this time, it had a duration of 5 seconds and it was the control condition. And there's 90 of these. One thing I forgot to mention for those who haven't used Python before is the first number is always 0. So if I say, you look, oh, there's only 89 of these, Rob, but you said there was 90, it's because we're starting at 0. And there's also many ways to achieve the same outcome, like with all toolboxes. So another way that you could look at the triggers would be to chain some of these commands. So here we're taking the raw data, we're asking for the annotations, we're converting it to a data frame, and then we're going to plot that as a scatter plot. And it should look like the plot above. So I'm just, you've got your control conditions and your tapping, and they're all randomly ordered. Another common way to manipulate your data, so there's resampling, and then there's cropping. But another thing that can be quite handy is to just pick certain channels. Sometimes you only want to analyze a couple of channels over a certain brain region. And so the way we do that is we pick channels. So here we're going to take our raw data, we're going to make a copy of it, and then we're going to pick channels 0, 1, 2, and 3. So we're just going to take the first 4 channels. And you can see that returned just 4 fNIRS channels, whereas previously we had 56. So this is something that I do quite often. Maybe I'll just want to take the long channels or just take the short channels. So I pick the channels that I want. That's the terminology that we use. And if you want to see where those sensors were on the head, so you can say pick the first 4 channels and plot those sensors, and we can see that they exist here. And there's 2 of them because each channel has 2 wavelengths. So that's why we've got 4 channels, but only 2 physical channel locations. And similarly, we could now plot the waveforms. So if we run this, we take the raw data, we make a copy of it, we pick the first 4 channels, and then we plot the first 5 minutes of it. It's the same plot that we had before, but now just with those 4 channels. So I'm just sort of showing you how to sort of manipulate and zoom into your data. And you could also just pick a single channel. If you want to look at just a single channel, you can just pass it a single number. And if you're playing along at home, you want to plot the first 10 minutes instead, you change that duration there. So this is just how you sort of examine your data. All right, so another thing that's quite handy is cropping your data. So let's say you started your experiment and then your participants started talking to you and they were meant to be doing the experiment and you want to throw away the first couple of minutes. That happens to me all the time. So we use the crop function, and you can give it a time to crop from and to, so that the minimum and the maximum time that you want to retain. And so you take the raw data again, we make a copy of it, and then we crop it between these 2 times. And so if I do this, we should only be left with 600 seconds, and we can see that's what happens here. So we're only left with 600 seconds of data. So that's kind of a convenient thing to do. So we had another question in the registration. Someone asked, what are the best practices for infant and juvenile fNIRS data analysis? So I would say, I haven't done a lot of infant analysis, but I imagine they move a lot. It's kind of, and I imagine there's sort of gaps of data where you want to ignore it because they were coughing or something, or they were just not doing what you asked. So just gonna go back up here to the interactive plot. And this is again, this is an advanced feature, but I'm just showing you because somebody's asked. These annotations here can be events, but let's say that you wrote down in your lab notebook that somebody moved between 150 and 200 seconds. You can annotate that data by pressing the A button, and you can manually add annotations. So annotations about where bad things happened or what data segments are bad. So if you had some bad movement, you can add this new label, and then you can click between 2 regions like this, and it's going to mark that as bad throughout the remainder of your analysis. So imagine if you had some infants and there were sections where they were moving, and you wanted that not to be included in your block averaging. This would allow you to do that. So you would mark it as bad, and then that information is retained through the entire pipeline. And then when you extract epochs or something else, that would not be included. But beyond that, I don't do infant research, so I can't really answer the question any better. All right, so that's all the kind of manipulation of data I was going to go through. Just checking the time. So obviously we need to do some signal processing. So, we've got the standard analysis, such as conversion to optical density. So here we're using the MNE toolbox, and then you go dot pre-processing, it's NIRS specific, and then dot optical density, and then you pass it the raw data, and it will return raw optical density or optical density data. So it's done that conversion. And then if we now look at that variable raw OD, I'm going to call it, it looks quite similar. It's telling you there's 56 channels. But if we skip that, so if we now convert it to BLM Law, so we're going to use the BLM Law to convert to hemoglobin, we would see we would see again that we've got 56 fNIRS channels. So this all looks the same, but if we look at the channel names now, we can see that the channel names now have HBO and HBR in front of them. So it's successfully converted the data to hemoglobin concentration. And we can do things like, before when we were picking channels, we would say, give me the first 6 channels. We can now do things like say, give me all the HBO channels, or give me all the deoxy channels. So you can pick based on that, which can be quite handy. So now if we plot the data, so this is the exact same command as before. We're passing it the raw hemoglobin values, and we're just telling it to plot it with the 5-minute duration. Oh, sorry, I forgot to convert back to. This is what happens when you jump around. This is what happens when you jump around. So now when we plot the data, it's in HBO and HBR, and so it's now plotting all the HBO channels in red and all the HBR channels in blue. Other than that, everything is still the same. So we've still got our triggers. It's remembered our bad movement section from before. So that's quite handy, and what can be quite useful is, let's say you just want to plot the HBO channel. So you'd say raw hemo, give me a copy of it. I want you just to pick the HBO channels and then plot it. If we do that, we're just going to get the HBO channels.
And is it possible to have HBO and HBR for a single channel at the same location?
Together, so yeah, so if I wanted to plot that, so instead of just picking HBO or just picking HBR, I might pick just maybe the first two channels. Oh, they're overlaid. So that is why in my next example, I show you how to change the scale of the plotting. So good question. So so before this scaling here is too big. So if you want to plot just these first two channels, and I've changed the scaling here, so you can tell it I want HBO to be scaled with this scaling. And you can have HBO and HBR scaled differently, or if you've got a mix of EEG and fNIRS data, you can scale them all differently because your EEG is on microvolts and this is on micromole. So you might want to scale them differently so that you can at least plot them all together. So if you wanted the HBR to be a bit smaller too, you'd say HBR equals 5 e to the -5, and all values within MNE are SI units. So that's why I'm using 10 to the -5. And so you can see it's rescaled that to be a more reasonable value. Keep an eye on the time, I've got 10 minutes. Okay. So we can also look at data quality. So again, you'd go to MNE, pre-processing NIRs, Scalp coupling index, and you would pass it, for example, the optical density data, and it would return the Scalp coupling index for each channel. We can plot that, of course. So most of these channels are good, and they have a few poorer channels. You can mark channels as bad. So this is similar to before we marked a time segment as bad, you can also mark an entire channel as bad. And I found this to be quite useful when we do cochlear implant research. You might have a channel that's over a device. It's clearly not measuring anything from the brain. So you can just mark that entire channel as bad. And so you can just give it a list of channels like this manually, and that would mark the channels as bad. And then if you just, again, you look at this information, it's now telling us that it's got these bad channels, and that is retained through the entire pipeline. I might skip a bit of this because we're sort of running out of time. I'm going slower than I thought. If a channel is bad and you ask it to plot the sensors, it will mark that in red to let you know. Yeah, sorry, I'm gonna skip to the waveform analysis.
We are good on time, Rob.
Okay.
We can go all the time you need. Please take it.
Okay, cool. Well, we can, yeah.
Very quick question. The Scalp index, Scalp contact index, coupling index. If you could talk very, very briefly about that, what is taken into account when?
Okay, if we're not rushing, definitely. Yep, let's go. So this, let's go up a bit then. So this Scalp coupling index here that we calculated, this is from the work of Luca Polanini, and they've created a few different data quality metrics, which we have them in the MNE toolbox. So there's a Scalp coupling index. So that tells you how well, or it's meant to tell you how well your sources and detector is sort of coupled to the skin. And it's looking for sort of cardiac activity within a certain frequency band, and so a high value would indicate that you have good coupling to the skin and you're likely to be measuring a brain response, and a low value might mean that something's not plugged in right, or you're over a hearing aid or something, and you're not coupled well to the skin. And so different papers seem to have different thresholds as to what they call a good and a bad channel. So here I might say, everything below 0.8, you might mark as bad, and so you're just throwing away the few worst channels. So we can also, so that's just looking at the entire signal, and calculating the scalp coupling index for the whole thing, but sometimes the quality of a channel can change over time. And so we can also look at the scalp coupling index over a windowed period. So we have this function here called scalp coupling index windowed, and we're telling it to give us a 60-second window, and it's calculating scalp coupling index over those different windows. And there's a standard plot that it creates here. And so you can see there's time along the bottom, which is chunked into 1-minute intervals. We have all the channels, and you can see that channels that were bad in this particular measurement, like this one here, tended to be bad for the whole recording. And that's, you know, that will depend. If you've got people walking around, a channel may become bad halfway through. This person was sitting in a chair quietly, so it was quite consistent. And then you can, if you give it a threshold on the right-hand side here, it's telling you all the time segments where that channel was below a threshold. And similarly as before, you can get it to MNE can automatically mark these channels as bad, but also it can mark that specific channel and that specific time as bad, and just throw away that single piece of data if you do some averaging analysis.
Mm-hmm.
And there's also,
we have, I'm sorry to interrupt again. We have a couple of questions on Beer-Lambert's law, if you would like to take them now, or
yeah, let's do it now. While I have a drink of water.
So basically, how much control do we have over the parameters we define DPF, etc., and can we change the parameters?
Yep. So the distance is calculated from the 3D locations of the sources and the detectors, and so you can to do the DPF, you can specify. So I'm just looking for where I did that. This would be a good time to show you the documentation. So if we go to MNE.tools here, and let's say you wanted to know about our Beer-Lambert law. So I would type in Lambert and into the search, and it's going to find the Beer-Lambert law function. And it shows us that we can specify the partial path length factor here, and its default is 0.1, which is I think the same as the NIRs toolbox, which was the most popular response earlier. I think the Homer toolbox uses a value of 6, something like that. And so so currently you can't specify the distances yourself. It's taken automatically from the 3D locations. And I'm also thinking about in the near future making this age dependent, but we haven't got around to that yet. But you could, you could do that manually. So you could set this value for each person based on that Shortman paper where they provide a sort of an equation, an age dependent equation. So a medium level of customization to answer your question. All right. Any other questions while we're at it that have come through that are relevant?
Not about Beer-Lambert's, but there's a question that has repeated a few times, which is about making copies of data. I'll read one of them to give you an idea. Do we have to make a copy of the data before each pre-processing step, or can we have one copy? It looks like you're always making new copies. Do you keep the previous steps in the copy?
Sorry, sorry, I did go over that too quick. I was just making copies because we were doing things like cropping to show you a point, and then I wanted to use the full piece of data again later. So in a standard pipeline, I would barely ever use a copy. And so we'll go through a standard pipeline now. So somewhere where you might want to make a copy would be, let's say you wanted to calculate the scalp coupling index just over the first 30 seconds of the measurement and pick the good channels based on that first 30 seconds, but you wanted to do your full analysis on the entire thing, that you would calculate the scalp coupling index on a cropped copy, but do your full analysis on the original thing. So that's probably one of the few places that I would actually work on a copy. So let's go through a basic pipeline now, and I'll sort of, you'll see that I'm not really using copies.
There's one more question, if I may ask, on scalp coupling index, since you mentioned it. Just a consideration that SCI should be used along with the peak spectral power metric to assess the quality. The SCI accuracy could be affected if motion artifacts exist in a channel. So,
yep, that's less of a question and more of a point out. But but I will point out that again, if we go to the documentation, so if we go to MNE I always go to the wrong link. If we go to the examples here, we have this signal quality evaluation example. And so in all the examples, we try to provide a list of relevant literature as well. And so in this example here, we calculate the scalp coupling index like I did before, but we also calculate this peak power metric, which you just mentioned. I'll make that a bit bigger. So the peak power metric can also be calculated in MNE, and you can use that to mark specific segments as good or bad. So if someone moves for a section, this might automatically detect that and then just exclude that segment of data. Does that introduce? Does that, I think, yeah. So I agree. Yes, you should definitely use peak power too. Is the answer there? All right, so we'll go through a basic pipeline now. So let's start again fresh. So now I've shown you all the bits and pieces, how to pick and crop and do all the rest of it. Let's do it to analyze some data. So we'll start fresh. So we're going to read our raw data again. Oh, I've used the bids here, but it's NIRx data underneath. And then we're just going to, so we're going to read that data, save it into the raw intensity variable. Then we're going to pass that through the optical density and then the BLM Law. And so that's done. And then for this example, we're just going to use the long channels. So there's a handy little function to grab long channels. So it's MNE.NIRs.channels.get long channels. There's also a get short channels, and you can specify the distance which you define as a long or a short channel. So the default for a short channel is 1 centimeter, and I think all the NIRx ones are at 0.8 of a centimeter. So that catches all of those. So now if we, I'll just put in this raw hemo here, we can see we've got 40 channels left, whereas above there was 56 channels, so that's done its job. And then what I like to do next is to look at the spectrum of the signal. So we can take that raw hemodynamic data and plot the power spectral density of it. And so I like to look at this, and that will, it knows how to handle oxy and deoxy, and that they're different things, and we'll plot them separately. And we can see in this example that there's an increase in activity around the 1 to 1.5 hertz. That's my heart rate. This is heat tapping in this. You can also see there's lots of low frequency content here and a slight bump probably around 0.1 hertz. So I find this quite handy to look at to make sure the data is okay. And here I passed in the average equals true argument, but if you were to pass in the average equals false, it's going to plot a line for every channel. And this can be handy if you've got a noisy channel or something that's not connected well. It will be a flat line. It won't have that heart rate bump, and it'll just be a flat line. And then the color here, you can see in the top, there's a color coding, so you can see where each color was on the head. It's probably a bit small. That's what it looks like. So yeah, this green channel here, which looks a bit different, you can say, okay, that came from the top left. So these are all default figures from MNE, which you don't need to teach it how to do it. It knows how to plot the data correctly. So the next thing we're going to do is to filter our data. So we take our raw oxy and deoxy data, we call filter on it, and we say we want to filter between 0.05 hertz and 0.7 hertz. Now this is, there's a lot of options for filtering. It's quite detailed. So if we were to go to filter, I can just look here for filter. just to show you the documentation. So you can specify the edges if you want an FIR or an IR filter, the filter length, the bandwidth, and so on and so forth. So I'm not going to go into that, but just so that you know that that's available. And so if we filter the data, it will print out the exact filter details that it used, which can be handy when reporting your data in a paper. And then if we plot the frequency content again afterwards, we can see that everything past that 0.7 has been reduced, and everything below that 0.05 has also been attenuated. And the little dotted lines show you where the filter cutoffs were. So now that we've read our data in, we've filtered it, we can chop it into little epochs and do an averaging analysis. So we'll ask the software to give us all the annotations or the events, the triggers, by using this events from annotations function. And it's told us that it's found all the events that have a control, a tapping left and a tapping right. And so if you're missing triggers or something, this is the place where you might see it. And again, we'll make the same plot as before just to check our data loaded correctly. We've got 3 different conditions and they seem to be randomly ordered because we've got time along the bottom and then the event condition on the top. So next, what we do is we now have the raw data and we have all the timing of the triggers. We can now epoch the data. So again, there's lots of options here. I'm just going to run through a few. So we call the MNE.epochs function, and we pass it the raw data and the event timing and the event names. And we're also going to ask it to give epochs that start 5 seconds before its trigger to 15 seconds after its trigger. So that's the time minimum and the time maximum. And a handy little feature is this reject criteria. So you can say, I want to reject all epochs that had a peak-to-peak value larger than 80 micromole. Or you could say, I want to have a different criteria for HBR than for HBO. And so you can define that here. So we're just going to reject everything that has a peak-to-peak value greater than 80 micromole in this example. And that's going to go ahead and create all our epochs. So you can see here, we had 90 triggers, it found 90 triggers, and it's created the epochs for that, and it's dropped 6 of them based on this peak-to-peak rejection criteria. And we can ask it to tell us which channels it dropped. So if we now have an epochs variable, actually I'll run this one before that one. So we now have epochs. So if we ask if we ask it what are the epochs, it's saying we've got 84 events, we've got 29 control, 28 tapping with the left hand and 28 with the right hand. And that these are, the time window for these is from 4.9 seconds to 14.9 seconds after the trigger. That's because we asked for 5 to 15, but because the sample rate doesn't exactly match that. And we can ask it to plot a log of what was dropped. So here we can see that channel S4D4 caused most of those peak-to-peak rejections, but in total we rejected 5% of the data. So that's how you would epoch your data. And then we can, if we want just some of the epochs, so let's say we just wanted to analyze the tapping data, we would call epochs.tapping, and it's now not showing me the control anymore, it's just showing me the tapping, but the left and the right. Or you could just ask for just the tapping with the right hand, and it will just give you the tapping with the right hand. So you can sort of chop in your data in different ways, like this. And so if we want to, we could then average all the epochs. So if we want to take all the tapping with the right hand and average it, we would call epochs tapping right dot average, and it will return what we call an evoked response. And then we could plot that evoked response. So this is the default plot for an evoked response. It will plot the oxy and the deoxy separately, knows that they're different things. And yeah, so that's kind of handy. And each line here is a different channel. And we can save that into the evoked variable. So there's different ways we can plot this. There's the plot that you just saw. We can also do a topo plot. So here it's showing you each channel in a different sort of in the layout that it exists. I don't find this. I normally have lots of channels, so I don't use this one very often. It gets too crowded. So what can be more handy is what we call a joint plot. So here we're going to chain our commands. So we're going to take our evoked response. We're going to pick just the HBO channels, and we're going to do this joint plot. And so here it's going to show you the waveform. Each channel is a different color, which is represented in this topo plot here. And then we've given it these times, and it's going to plot the response over the head for those times. And so this isn't a very interesting example, so the whole head lights up. But let's say you just had the auditory cortex and you're playing a sound, the visual cortex might not light up. And so you can kind of get an early look at your data this way. So what I normally like to do then is to, with an example like this, where all the channels are relevant, just make one giant region of interest. We're going to average all the channels together, and we use this plot compare evokes function. And to do that, we need to tell it the evoked responses. So this is a little complex, but there's an example that walks through this in detail on the website. But we create a dictionary, and we can pass in as many conditions as we want. So if we want to do just the tapping HBO data, we say tapping HBO is equal to the epochs. All of the tapping, I want you to average it, but just the HBO channels. And if we run that, we get a nice clean hemodynamic response. So this is basically just the average of this plot up here for HBO. But normally you would want to plot HBO and HBR. So we run basically the same command here, but below. So we're going to say tapping HBO is my tapping epochs, but just give me the HBO. The tapping HBR is the tapping epochs, but just give me the HBR. And then I also want the control HBO, which is just the control epochs. Pick the HBO. And then so that will create a larger dictionary. And then if we pass that to the plot compare evokes now, but we're also going to tell it that we want the colors to be HBO to be red, HBR to be blue, and that we want the control to be dashed. And we pass all that information through. We can see that for the tapping conditions, we get a nice clean response, and that the HBR has a slightly delayed negative HBR, and we can see that the control is, it's just wandering around. That's what we want. And I've probably got another 5 minutes left, so if you're thinking about leaving, stick with me. And so we also have some other nice plots, so we can do this plot image. So if you take your tapping data, you make a copy, because I just want to pick the HBO channels, and then I plot the image. It will show you the average response, but now we've got a 95% confidence interval plotted on top of it. And the plot above is, so we have time, and then we have the epochs, and you can see that the response from every epoch individually. And this can be handy if you think your person fell asleep, or if you think there's some effect of time throughout your experiment. So maybe you get large responses and then it habituates out or something like that. So you'd be able to see that in a plot like this. And then for the control, I mean, you can see it, while it wandered around in the plot above, when you put confidence intervals over it, you can see it doesn't really vary from 0. So the last thing I'm going to show you is just how to quickly extract some metrics from your waveforms and to do a quick statistical analysis on it. And I'm aware that I'm 10 minutes over. So we're just going to look at the tapping data. So we're going to take all of both the left and the right hand together for this example. And we're going to create a data frame. So a data frame is just like an Excel spreadsheet or a CSV. So you've got different columns of information. And so we're going to ask, we're going to loop through each of our epochs, and we're going to crop it between 4 and 6 seconds. So let's say, we were tapping for 5 seconds. So we want to take the peak value of this epoch here. We want to do that for every individual trial. And then we want to compare that to the control condition to see if they were different. So here what we're going to do is we're going to say for each epoch within all of our tapping epochs, I want you to make a copy, pick just the HBO channels and crop it between 4 and 6 seconds. And then I want you to take the mean of that, and we're going to times it by 1e to the 6 to get it into micromoles instead of moles. And then we're going to store that in a data frame. And so if we run that, we can see that it creates a data frame, and that for the condition, we get a bunch of different values. And then we can append the control in the same way. We can save additional information. So the participant's ID, and we can save that to a CSV file, and you can run that in your favorite stats program, but we'll run it here. So you're going to get a table that looks like this. You're going to get a table that has the condition, what value it was, and the person ID. So if you had a study with many people, you would just grow this data frame to do your stats. And so to do those stats, we're just going to plot it. And, so we use this package for plotting statistical comparisons called, I don't know how you meant to pronounce it, but in my head it's the best. And we're going to say we're comparing control and tapping, and on the x-axis I want to plot the condition, and on the y-axis I want to plot the value. And it will make a nice little plot like this. So here on this plot here on the x-axis, here are the 29 trials from this one individual, and each of the extracted response sizes or amplitudes. And then we have, for the tapping data, we have 55 data points. And they're all plotted. This is the extracted oxyhemoglobin between 4 and 6 seconds. And then it's done a bootstrapping resampling, and it's found the confidence interval of the difference between these two conditions. We can ask it to tell us if there was a difference between the control and the tapping, and indeed there was. So the mean difference was 12.5 micromole, and it was highly significant. Or if you want to do more traditional stats, you can just use this package called SciPy, and in that stats package, we take just the tapping and just the control data, and then we can do a one sample t-test on the tapping, comparing it to 0, and we see that the p-value is extremely small. So the tapping there was a significant tapping response, and the control is the p-value is 0.3. So there was no significant response to the tapping to the control condition. Now I'm aware that I moved very fast through the end there because I was over time. I apologize. Please take a look through the examples if you've got additional questions, or get on the forum or email me, or in seminar too. If there's anything that I didn't cover well enough, we can go back over it. But yeah, thank you.
Great, wonderful. We do have a lot of questions actually, but
so people will listen. Good.
It seems that most of them will be answered in the part 2, where we talk about more advanced topics. So Rob, I'll try to take a few general ones that relates to what you talked about now.
Yep. And please take a note of the extra ones so that I can make sure I do cover them in the second talk.
Absolutely. So in the second talk, then we could do a little revision of the first talk, answer the question, and then. Yeah,
and in the second one, I won't be introducing what a function is in Python. We'll jump straight into the details. Yep.
Okay, I'll ask some quick ones. Is PPF same as DPF in MNE?
So maybe I should have used the term DPF there, because yeah, PPF normally doesn't take into account distance, right? So that's an error. I will fix that before the next seminar.
Great,
Yep.
thanks. Okay, can we mark channels as bad based on SCI instead of manually choosing channels?
Absolutely, absolutely. So there's an example on how to do that. I mean, let's just pull up an example. So you could find an example of how to do that in the waveform averaging analysis example. And in this one, so here is the same code that I just showed you before. I mean, all the code that I showed you is chopped and taken from different parts here. So here you calculate the scalp coupling index. And what we can do is we can say, set the bad channels to everywhere where the SCI was less than 0.5 or 0.7 or whatever you wish. So it can be calculated. You can run it like that. You can also, if you want to do it with the windowed section, so that function, that windowed function, where is it? So the signal quality evaluation example. So let's say, let's for interest's sake, say you're looking at peak power instead. This peak power function here, if you click on that, it has a threshold too, and by default it's disabled. But if you use that threshold, every section that is below the threshold will be marked as bad, and that can be quite interesting because, say for example, here I introduce some noise, so I purposely add 2 artifacts. And then if I run the peak power on this, you can see that these 2 artifacts appear. So it won't mark that whole channel as bad, and it won't mark that whole time slot as bad. It will just mark that particular channel at that particular time as bad, which can mean that you get a different number of epochs per channel. If that might be, depending on your analysis, this might be a good thing or a bad thing, but that functionality is there. So if you're really struggling to get enough data, sometimes it can be handy to not throw away all the channels there and just throw away the one channel at the one time slot that was bad.
Makes sense. Okay, I think you're going to mention short channel regression in the next one.
Oh yeah, but within the context of this averaging analysis, there is different short channel options. So for the GLM analysis, which I'll present next time, you can include short channels as regressors of no interest. But in the sort of averaging approach, we have that sort of Sager and Berger short channel correction approach. So there is a, do I have a tutorial on that one? Yes, in the signal enhancement techniques tutorial, I run through how to use the short channel correction, and I think it's also discussed in the Shulkman 2014 paper. And it's the same approach which you guys provide in your MATLAB code. It's the same sort of underlying technique. So there's this it's called short channel regression, and you can find the references that I used to write it here. So it's available. I didn't have time to run through it today, sorry.
We also talked about this in another webinar, which was about analysis of short channels data in detail. So could always
great.
go back to that, right?
Yeah, it was. I watched that seminar. It's the same technique that's done here. Yep. Okay.
Super quickly, options we have for motion artifact and systemic activity correction.
Yep. So for systemic activity correction, I mean, I know use some sort of short channel regression, either this one for my block averaging, or in the GLM, I like to include a regressor of no interest. For movement correction, so there's you can either exclude sections of movement based on what we were talking about before, but we also have the TDDR, which I find to be really pretty great. So there's an example of that in the artifact correction techniques. here. So in this example, I load some data which has some small movement artifacts, and then I introduce some artificial ones, a spike artifact and a baseline shift. And then I demonstrate you can use this temporal derivative distribution repair to sort of remove them. And it sort of shows you what it looks like before and afterwards, which, you know, there's something that's left there, but it's definitely much less than if you were to filter after this or do something, it would be much better. So yeah, I think we have the TDDR. Yep.
Okay, let's take one specific one. Maybe this will help them to use the toolbox properly. I have a question regarding the 0.0.5 version of MNE. Try to read data from a NIRs Port 2 device. The code in your GitHub seems to support this, but the code from the pip wheel doesn't. Can you say when the wheel will be updated?
Okay, yes. So so MNE is you know, I don't run it. It's been around for many years, and it's run. There's a group of maintainers, of which I'm one, and so every time we submit code, like I can't submit code automatically. I have to submit code, and then somebody else reviews it, and it gets checked. So there is a slight time lag between code being submitted and it being available. And the benefit to this is everything is checked, and there's tests for everything. And so we normally have what we call a development version, which is like cutting edge, and that's what this question is about. So this person is using, they know that this reading this data is available in the cutting edge branch, but it's not yet been released. And so we do releases approximately every 6 months. I'll chase up when the next one is and find out, because it would be handy if people could do it. If you want to install the cutting edge version, which is no problem, you can do that. So you can type in like pip install MNE, and that will install the stable version of MNE. But if you go pip install and you provide the git the git address, so if you provide this address here, so you go pip install and you paste this, it will give you the newest version, and that will allow you to read the data. So that that's how you'll get around that problem. But otherwise, yes, there's always a stable release every once in a while, and that release, the reason that's handy is because let's say you've got a longitudinal study that goes over 3 years, and you want to go back to the analysis that was done exactly 2 years ago. We have these stable releases, and it's not going to change from underneath you. You can always go back to a previous version.
Okay, wonderful. Rob, it's going to be what, 2 a.m. in the morning for you, so I have to let you go.
I mean, I can keep taking questions. I mean, I'm pretty. It's up if you got someone. I mean, yeah, I'm happy to take more questions.
I think we have covered most of the general ones. Cool. There will be some, I'm sure, will be answered in the next one. So
great.
We're good for now. And again, if you have missed anything, people can always write to us. We can contact Rob, or you already provided the support at RIS. And that's it. Thank you so much. This was wonderful. Judging from the reaction of attendees, I think everybody liked it very much. And we look forward to having you for round 2.
Thanks for having me. That was great.
Thanks, everyone.
Thanks, Michael.